the third of the three fundamental algorithms is going to be Dijkstra's algorithm. Actually, but I did promise that we'll take a break now, so this is a good time. So let's just take 10, and we'll come back and do Dijkstra.
It's one of the angle addition and subtraction formulas that you have to use. And then eventually it'll work out nice because that pi 4 is known, but just pretend at first that's a variable. And then use the sine addition angles. Yeah, angles and difference formulas.
I did
Just use this.
I got this cost.
Here would be x and here would be pi 4. And then once it gets to this, then you can
I use this one instead of this one. The crust. The cost. Yeah. I have to do this. So I said it went from 1, 2, then 2 again, 3. And then the cost for all this is 1, 2, 5, 8. So what's this will be 1, 3, 5, and 8. So it goes for 8. And it's the same, but it keep end up being the same tree. It's the same pattern, you know. Okay. 3 also, okay. It just happened to be the same. So what is the difference between the two? The same I mean, other than we just do that, but then I guess we just circle up. I don't know what the difference is. I guess I'm trying to figure out the difference. Because we end up with the same cost.
Yes. First one, actually, you are taking from the whole graph and taking this side.
Yeah.
And this one actually.
Yeah.
But
yeah. Yeah. Okay.
I took the beginning. I'm not worried about it. Actually, not really, because I worked it out that I come back, there's a 4-day, and then there's only 1 day. And I figured by that day, before we start class, there's no point in sold over your time.
Hey, there's going to be a urinalysis on the 3rd, so be sure not to stop doing drugs.
Yeah, exactly. I'm going to do cocaine up to the 1st. I'm going to stop.
I'm trying to tell you guys, if you're sitting around the house, with your mom and dad, passing the news, you just go pass.
There must be something magical about urine at 4 in the morning that we've got to do that at that time.
You know what I'm saying? You can't miss class.
It's called suck fast.
We can miss class for.
Actually, this shit. Actually, isn't the truth of the matter like that's the worst time doing your analysis because like you wake up and pee. You wake up and pee, but 2, like if you don't wake up and pee and you give them that sample, then it's a bad sample.
Because it's stored in your kidneys all night, or you don't drink your bladder.
Oh, because it's the most filtered.
Yeah.
It's the most filtered.
Oh, so most of them, because heck, that's what because like when they call me and whatnot, I make a point not to go pee that morning, like when I wait, like if I get there o'clock, before I go to the bathroom.
What's the decision? There's going to be a lot of people out there. If you don't go first,
No, it's going to be in the reserve headquarters. Last year,
yeah.
It's like big giant reserve headquarters building, like 15 stalls, and then they have like 30 figure waters.
I'm just going to do it.
How did I not have to do that? Have any recollection?
You just didn't do it.
Yeah, it's like you
You know, he just said, don't just say this.
Oh yeah, you need to be there. Right? It's just fun to tell soldiers, like you hear the incidents, tell people, be there 5 to 10 minutes early. And the organization officers, we tell everybody to come about 30 minutes early.
Yeah, I'm sure if you dug into it, though, they talk about some more officers that, with or some
Because mass punishment for an event 7 years ago is still, that makes sense.
That's still relevant.
Yeah.
Some guy drove to Atlanta when he was supposed to be there 10 and 11. So he couldn't make it.
That keeps happening.
I just want to point out that was major.
People were supposed to be
It was major. It was major. That
There's almost as bad as a ball.
get up there and brief that you need to sign in by 0:23:59.
There's errors all over this thing.
Who's going to do that?
Yeah, he was hurt.
Yeah. I'm pretty sure he was half drunk as they're speaking. I'm going to be honest.
You know, the other thing was, like, man, did you do much public speaking? Because you just seem kind of nervous.
Yeah. I'm pretty sure he had liquid lunch before he got up and briefed.
That's a lot of liquid lunch. That guy's running.
Yeah, that's true too.
Power hour. That's what he did.
Like, you ever hear how much, like, Andre the Giant used to drink?
No. I can imagine.
They didn't even know how to, like, when you do backstreet on him, they had no idea how to.
Get him on the bed or
Yeah. And he's giving them, like, you know, like, gallons of vodka that he drinks a night.
Jeez. Yeah.
I guess don't take around with the guy.
Yeah.
I don't think you should be allowed to drink.
Can you imagine like owning like a mom and pop like restaurant that's got like some buffet and he walks in? We're closed. When'd you close? When you walked in.
They can start weighing the plates and paying like takeout.
Yeah.
4 pounds, $7.
I don't know, though. He's Andre the Giant. He's such a really nice guy. I'm sure if he gave him good customer service, he'd probably give you a big enough tip to make up for that.
Or he would
He'd just
be out of your clothes and choke slam or whatever it was.
That's true. And if there's any folding chairs in there, you're done.
Your only hope is that you're the one guy that's able to body slam him. That was the kryptonite.
Which has never happened.
No, Hulk Hogan did it.
Yeah, because
Who else did?
he jumped in.
Yeah. I can't remember. Wasn't it like Big John or somebody like that? That
One of the
also
guy just built. Remember
body slam?
who's the guy that's like biggest built? It's been like 5 or 6 days.
Dude, I used to watch a lot of wrestling growing up. Wrestling. Not wrestling.
The question is if you believe it was real or not. That's the.
Yeah.
Yeah. The question is, did you believe it was real after you found out Santa Claus didn't exist?
Yeah. Wife's like, because every now and then I'll get a kick and I'll start watching it again for a little while. She's like,
it's a
what are you watching? Exactly. I'm like, it's like a soap opera for men.
My stories are on. You should tell your wife.
Thanks for our lives.
We're not going to resolve this.
In a cage.
We're going to resolve this. So, shortest path problems you can imagine with all the things that these are good for. So, finding the best route to your destination, Google Maps, finding the best way to route a packet through a network, finding the best route to send trucks delivery trucks, so they save the most gas and so forth. So there are all sorts of good reasons to find the shortest path between two nodes. So here we've got a network, and each edge has a value, which again we'll call its cost or its length, propagation time, one of those three. They're all pretty much the same. We'll use the word length because then the shortest path will have the smallest sum of edge weights. So we call that the shortest path. So length is the metaphor we'll use. All right, so what we're going to do is determine the path of least length. And technically, this really should be determine a path of least length because there may be more than one between two vertices. So it turns out that there are a couple of different algorithms to do this, and they all do the both of them. Well, okay. The first two, they actually find shortest distances, shortest paths between some start vertex and all other vertices in the graph. So you get sort of all the shortest paths at one time from a particular single source. These are sometimes called single source shortest path algorithms. And the two of them are Dijkstra's algorithm, which is the most commonly used. It assumes positive edge weights. So the edge weights have to be positive, they can't be negative. And then Ford's algorithm, which allows negative edge weights as long as you don't have any negative cycles. So a cycle with negative total weight. Because if you have a cycle with negative total weight, there is no shortest path, because you could just keep going around the cycle any number of times and, rack up points or whatever you're racking up. I guess if it's a cost, a negative cost would be like you get something by traversing that edge, and you just keep traversing it. Okay. So no negative cycles, but Ford's algorithm can have negative weight, so it's more general than Dijkstra's, but it doesn't run as fast, and it's a little more complicated. All right. So these are called single-source shortest path algorithms because they find the shortest path from a source to any other vertex for all other vertices. What if you wanted to find shortest paths and shortest distances between any pair, not just single source, but any source and any destination? Then those are called all pairs shortest path algorithms. And the one we'll talk about is Floyd's algorithm, also called the Floyd-Warshall algorithm. And this is an all pairs shortest path algorithm. So it computes all pairs at once. Now you could always just take a single source algorithm and then just run it repeatedly on every source, right? And then you get all pairs that way. But this actually, Floyd's algorithm runs faster than repeating, say, Dijkstra's algorithm n times. All these algorithms work on directed path, work on digraphs. By the way, they work on both. They work on digraphs and undirected graphs. You can always represent an undirected graph by a digraph as follows. If I have an undirected edge and I want to represent an undirected edge and all I can do is a digraph, then the way you represent that is just by a pair of directed edges, like that, going in both directions. This really captures the fact that you can traverse the edge in either direction. You can traverse an undirected edge in either direction. So digraphs in that sense are more general. If your algorithm works on a digraph, it also works on undirected graphs because you can always represent an undirected graph. That's just a special kind of digraph. So these algorithms run on digraphs. So the shortest path from, say, node S to node T might have a different length than the shortest path from node T to node S because it is a digraph. All right. There is an algorithm to find the second shortest path in the network, and that's Pollak's algorithm. We'll probably skip that. We will skip that for sure. All right. So before we do Dijkstra's, we're going to do Dijkstra's, and then we're going to do Floyd's. We're going to skip Ford's. But before we do that, what we're going to do is we're going to find shortest paths where all the edge weights are just the same. They're all, say, unit weight. So this is sometimes called the unweighted shortest path algorithm, where all you're doing is counting the number of edges in the path. That determines the length of the path. And the way we're going to do that is by doing something called, well, doing an example of what we call graph search. In graph search, you start at some vertex S, some start vertex S, or source. And then from S, you systematically explore all the vertices that are reachable from S by some path. Okay. So the idea is that if you're at a vertex, you can follow edges forward easily. And by doing that in a systematic way, you can explore, you can visit all the vertices that are reachable from S, and then do some computation on them. So there are several kinds of graph search. The one we're going to look at is called breadth-first search. This is what will give you an unweighted shortest path algorithm. So here's what breadth-first search does. You start at a vertex S. So we're going to assume the following about the graph. If you're at a node, it's easy to find the nodes adjacent from the node you're at. So if you're at a node U, it's easy to find all the nodes V that are adjacent from U. So initialize an empty queue, a regular FIFO queue, now as a data structure, and we'll call that Q. So what we're going to do is we're going to mark S as the source and insert it into Q. So this above this line is initialization. So the repetitive aspect of the loop is right here, of the algorithm. So you're going to do the following while Q is not empty. You remove a vertex. You remove a vertex from Q, call that vertex R. Now when you remove from a Q, what order are you removing?
First in.
Yeah, first in. So first in, first out. So you remove things in the same order that you add them. All right. Now what you do is you, for each unmarked vertex adjacent from R, you mark Z as coming from R and then insert Z back into the queue. So here's what you do. Here's R. Okay. And let's suppose X, Y, and Z. So you've got three nodes adjacent from R, X, Y, and Z. You mark each one of these as coming from R, and the way I'll do that is I'll put a red edge, a back edge, pointing back to R. What that indicates is that you found these edges by coming from R, following an edge from R. So that tells you where you came from. And then you insert X, Y, and Z into the queue in some arbitrary order. Okay, doesn't matter. That's called breadth-first search. And the reason why it's called breadth-first search is that because it's first in, first out, you will go through all the neighbors of the source. So the source is right here. Yeah. So there's S. Maybe that's T, U, V, and That's X, Y, Z, W, say. Okay. Breadth first means first you do S, and then you're going to process all the neighbors of S before you get to neighbors of neighbors. So the neighbors of S are the things adjacent from S, so that's T, U, and V. So the Q is going to look like this. I run it on this. Here's Q. It starts out with S. Then you remove S, and then you add, say, T, U, and V. Okay. When you remove, and these are marked, and so these come out, so T comes out next, right, because it's next in the queue, and what do I put in? X and Y, but I put them after U and V, because U and V came in first. And so the next thing I pull out is going to be U. And for that, I'll put in Z, and then the next thing I pull out is V. So I actually, even though I had X, Y, and Z in the queue, I go through the neighbors first, and then I hit the neighbors of neighbors. That's what the queue does. That's the effect of the queue. So what you do is you are visiting all the nodes of distance 1 from S. Those are the neighbors. Before you pull out anything of distance 2. So the nodes will enter and exit the queue in ascending order of distance from S. Okay, you'll get S is distance 0 from S. These are all distance 1. And then these are going to be distance 2. So we can augment this. That's the basic search algorithm. We can augment this as follows. Let's say each vertex has a distance attribute. Call it D, S dot D. So think of D as a distance attribute of S. We're saying the distance from S to S is 0. When we remove, when we add a new vertex Z coming from R, when we do this, we also set Z dot D gets the value R dot D plus 1. Okay. Because R is a certain distance, you then follow one more edge to Z. Z is going to be one further out. And this is guaranteed to work. This is guaranteed to give the shortest distances of all vertices. Okay. So it does two things, actually. So it finds the shortest distance, and it also allows you to recover the shortest path, because I have these back edges, these marks, that say where these things come from. Okay. There could be other green in here, I guess. I mean, it could be something like that going on. But you see, by the time I get to V, and I look at Z, it's already marked. So I just ignore it. So notice I only look at the unmarked vertices that are coming from. So look at the red edges. If you ignore the arrows, they actually form a tree. Well, if you put the arrows in and you think of the tree as having a root at S, and all the arrows from any node are going to point along a path to the root, then each path to the root is the shortest path in reverse. So the shortest path from S to Z, for example, is, well, you start from Z, follow the red edges back to S, and then you just run those edges in reverse order. Those will be the green edges, which point in the opposite direction. You run those, so the reversal of the red path gives you the shortest green path this way. So this does two things. It tells you what the shortest distance is. It also tells you what the shortest path is. Now, maybe you don't care about one or the other pieces of information, in which case you can just leave that part out. Okay, you don't have to include it. Might make your search run a little faster. All right, questions on depth first search? So if I give you a graph and I ask you to run breadth first search. Depth first search is the opposite. And I ask you to run breadth first search at a certain node, you would be able to say, give me the order that items come from the queue and give me the back edges as well as the distance values. You should be able to give me those two things. Okay. That makes sense? We often, coming from R, we often use a different attribute for that. We would say z dot pi gets the value R. Pi just means predecessor. Pi for predecessor along the shortest path, or along the shortest path from the source. Okay. It also might stand for parent. I'm actually not sure. Parent in the tree. All right, but anyway, the red edges form a tree. It's called the breadth first search tree. So keep this in mind. So breadth first search is generally useful for finding unweighted shortest paths. Dijkstra is going to find shortest paths in a weighted graph, and in some sense, it's also an example of graph search. But it's not quite as simple as breadth first search, because now we have edge weights we have to deal with. And so what we're going to do is we're going to have a queue, but it's not quite going to be a FIFO queue. Oops, okay. I actually wrote it down. Oh, good. Okay. So I can erase this. I forgot that I did that. Okay. Oops. Yeah, there we go. So it's all in there. Questions? Okay. Dijkstra's output. I think it's probably better to run a full-blown example while we're looking at this, because you can read through the text of the algorithm and just, read it like 3 times and just, what the heck is going on here? So I might just easier to start with an example. So I got 6 vertices here. Okay. And let's put in some edges with edge weights. So, maybe that's, 6. And that'll be 2. And that will be 5. And that will be 3. Actually, let me make that a little bigger. Let me make that 7. No, never mind. I don't make it 3. I was right to start with.
that.
Okay. Is that enough? Probably. Put one more in here. All right. So in Dijkstra's algorithm, we start with a source vertex. So we can choose a source. Let me choose E as the source, just arbitrarily. All right. So here's how the algorithm works. E is equal to what you're going to do is you're going to assign labels to every vertex. And as the algorithm proceeds, these labels might be updated. But eventually, a label will become permanent, and it will never change. And so the easiest way to track how this algorithm is working is by a table giving the labels of all the vertices. So let's just list these in alphabetical order. Label for A, label for B, label for C, label for D, label for E, and label for F. And here's the step. So step 0 is initialization. Can you all see that? All right. We're starting at E. So here's what happens. E gets label 0 and a blank. So this corresponds to the D attribute and the pi attribute in breadth first search. The D means distance from the source. Pi means predecessor on a path of that distance. Okay. So currently, all we know about is E. We haven't explored anything else. So what we're going to do is have all other labels be infinity. Infinity, a distance of infinity means I have not found any path at all from the source to this vertex. So for all I know, the distance is infinity, which means unreachable. So a distance of infinity will mean that that a vertex is unreachable from the source. If the graph is not strongly connected, that's possible that you might have vertices like that. But as far as we know, S is the only thing, E is the only thing we know about. The distance from E to itself is 0. Doesn't follow any edge. And it has no predecessor because it's an empty path. But all the edge weights are positive. That's what makes Dijkstra work, and that's important. Dijkstra actually breaks down if there are negative edge weights. All right, so here's what you now do. Look over. You do this now. You're going to do this in every single step. Look over all the labels. Find the smallest one, the smallest D value. It's the number on the left. Make that label permanent, and now start at that vertex and explore its neighbors, the things that it's adjacent from. So what's the smallest label? 0, right? That's always going to be 0. So this is the source. So I'm going to put a box around it and say, okay, this label is now permanent. It's never going to change. But now here's what we do. We go and explore the neighbors of E, the label we just made permanent. And if we find an edge that allows us to revise the label downward, then we do that. So, for example, we have we have an edge of length 6 from E to F. Okay, so I'm going to label these things. So this is 0. When a label becomes permanent, I'm going to mark it in red on the actual graph. Okay. So what do we know about F? There is a path of length 6 from the source to F, following this edge, right? So what's the current label of F? It's infinity. Well, now we found a shorter path. So here's what we do. We revise this label downward from infinity to 6. So in the next step, in step 1, this is going to be 6 now. And we record where it came from. That edge to F came from E. So we put an E there. See that? Okay, what else do I have? What else is coming out from E? A and B. So I'm going to do the same thing simultaneously. So A is currently infinity. I now see that there's a path of length 2 from the source to A. So this is going to be revised to 2 coming from E. And then B, even better, 1 coming from E. All right? So far, so good? Okay? All right, good. And the other labels are not reachable. They're not neighbors of E. So C and D are not neighbors of E. So I just copy their labels. I don't update them. So I still haven't found anything yet. And once a label is permanent, it's going to stay the same. So there's no reason to just copying it. I'll just leave it like that. All right. Now, among the temporary labels, what's the smallest? You always do this. You always pick the smallest one. B. That's the next one you make permanent. So it all boils down, what is the next label you make permanent? The one that has the smallest value. And that's kind of the greedy aspect of this algorithm. It's another greedy algorithm. All right, so B comes from E by length 1. So now look at B. So I've just made that permanent, so I now look at the neighbors of B. What are the neighbors of B? C. There's just one C. Okay. What's C's current label? Well, it's currently infinity. But now, what do I find evidence of? 6. Why is it 6? Because I forgot to add this. It's the distance from E. So B is actually, this is the true distance, the true shortest distance from E to B in red, because we've made that label permanent. So this is in fact the correct value. So if this is distance 1, and we now follow an edge of weight 5, that means we found a path from E to C of length 6. However we got from E to B, and then add one more edge in, that gives us a path of length 6. So very important, don't update it to 5, update it to 6. So, what am I doing? C. So this is going to be 6, and where does it come from? B. B. Bravo. All right, and that's it. All the other, that's the only neighbor.
So Dijkstra's is just one directional if they're directed?
Yes, you follow edges forward. You don't follow them backward. Unless it's undirected. If it's undirected, you can follow them in either direction. But it's the same algorithm. Okay, so this gets copied down. This gets copied down. And this gets copied down. Okay? So that's step 2. So again, we look and we say, well, what's the cheapest? What's the smallest label? A. Okay, that's the one we make permanent. So that is now permanent. And what do? We look at the neighbor from A. We look at the neighbors of A. There's only one neighbor. It's B. And B is already permanent, so we don't do anything. If a neighbor's label is permanent, we just ignore it. We're not going to find a shorter path. So we just copy down everything else. Right? So 6b infinity 6e. Okay. Now, which is the cheapest? It's a tie. As always, as we've done all through today, if there's a tie, what do we do? Yeah, whichever one you like. It doesn't matter. I'm going to choose one, though, and I'm going to choose F. I'm going to make F permanent. All right. If I make F permanent, then what do I do? So there are only two temporary labels left, C and D, and F is actually adjacent to each of them. So how about C? Oh, sorry, I got to mark these. A is 2E, and F is, this is 6E. So what about, so I go out from F and look at its neighbors. Its neighbors are B, C, and D. B's already permanent, so I ignore it. And that leaves C and D. So do I update C?
No, there's more on space.
Yeah, I don't, because C already has a label of 6. If I were to update C from F, I take 3 and add it to 6 already to get 9. You never update upwards. Okay? You already have a shorter path to C from the one you're going to get from that edge. So don't update. Just leave it as 6. So this is still 6. How about D? Yeah, well, D is infinity, so this is certainly going to do it. So D now becomes what?
16.
16. Coming from F. Okay, great. I'm running out of board here. Can you still see? People still see this? So which is smaller? Smaller. 6 is smaller, so that's the one. Oh, I'm sorry. This is now. Oh, I already did. Okay, so this is now permanent. I'll go up here, and this is 6 feet. Okay. So I only got one thing left, and that's the D. Only one neighbor. So 6 plus 4 is what? 10. Is that less than D's current label?
Yes.
Yes. So I'm going to update this again. So what do I put? This is now 10 coming from C. Whenever you update a label, you always come from the thing you just made permanent. All right. So I forget F. I forget this because it's not an optimal path. So just the F goes away. Just erase it and replace it with C. All right. Now I only have one temporary label left. It's clearly the smallest, so I make it permanent. If there are no other temporary labels, we're done. That's the whole algorithm. Does that make sense? So what you're doing is the D value, the numerical value, is the distance to the node that you currently know about, the shortest distance that you currently have evidence for. And what you do is you just go through this systematically, and the whole key of this algorithm makes it work is whatever temporary label is smallest, that turns out to be the correct value, and you make that permanent. Now that's, again, there's one can prove that. That's always this algorithm actually is provably correct, and it's crucial that you just pick the smallest of temporary labels to make permanent. And as long as the edge weights are positive, you will get at this point shortest paths and shortest distances both from E, the source, to all vertices. So I got to put this in. This is 10C. So let's draw in the back edges now. So for example, F is 6E. It comes from E, so I'm going to draw the back edges. Because that's an E, I'll just draw it back to E. This is E, I'll draw it back to E. That's E, I'll draw it back to E. That's B, I'll draw it over there. That's E, I took care of it. This is now C. That is also a tree, just like with breadth first search. It's called the, I don't know, I guess it's called the Dijkstra's shortest path search tree. I don't know what its name is, but it is a tree. And all the shortest paths are along this tree. You just follow the red edges backwards. And you get exactly one path from E to each node that way. All right. Questions on Yeah.
I noticed you chose B to start with the red, just by looking at it and seeing that it has some of the shorter paths directly connected to it. Is that kind of like a shortcut?
No. You don't have you usually don't have a choice of where to start. You're asked to start at a particular place.
So you'll tell us where.
I will tell you where. Yeah. I chose E. I chose E because I wanted to exercise some of the updates and non-updates to go on that can happen. So that's really Dijkstra's algorithm. I mean, you can maybe you can go and stare at the actual code, stare at the actual description of the algorithm, and it might make sense to you now. Okay, but I'm going to not do that. Okay, and I'm going to skip that example because that example is at least as good, if not better. All right. Distance matrix. I don't know what that is. Never mind. Oh, I know what that. I'm sorry. So the adjacency matrix. Sorry, yeah, I should mention this. How do you represent a network as input to an algorithm? It's just like an adjacency matrix, except that instead of 0 or 1 in an entry, you put the actual weight of the edge, if it's there. And if the edge is not there, you put some default value, which might be infinity, it might be 0, depending on the application. It might be minus infinity. And here, if there's not an edge, then we say it's infinity because the cost of actually going directly from this to there is infinity, which means it's impossible. You can't do it because there's no edge. That's kind of what infinity means. Okay? All right. Questions on Dijkstra? You could do Dijkstra? All right, you will do Dijkstra.